Okay, I'm going to talk a little bit about electrostatics and electricity. I'm going to go pretty fast because you can always go back and re-watch the video. One of the big things here is that electricity is a whole lot stronger than gravity. But there's always a repelling force just as strong to repel it. One way you could look at this is if someone were falling, gravity is, attracting them or accelerating them toward Earth, and they're going to hit the ground. Well, what's really happening there is that the electrons on the ground and the electrons from the body are repelling each other. So electricity is much stronger than gravity. The person won't keep going because of gravity. As you know probably from ninth grade science, that electrical forces come from the electrons that surround the atom. The outermost electrons can be removed, so you probably looked at this again in ninth grade science, that if you rub across the floor, those electrons build up, they come off the carpeting onto you, and if you touch something, you discharge that and get shocked. So again, you're negatively charged because you've gained electrons from the rug, and now the rug is positively charged. But as you know, these things go around back and forth, and they equal out. Gravity, Newton's law of gravitation, which we've looked at, is that force, the gravitational force, is equal to this g, this constant, times the mass of one object times the mass of the second over the distance squared, or the radius squared, the distance between the two objects. Well, interestingly, when we look at Coulomb's law, the law follows the same principle, which is kind of interesting, that the force in newtons again between the charges, and Q1 and Q2 are the two charges, in coulombs, divided by the distance between them squared, is going to determine the force of attraction or the force of repulsion if they're both positive charges or both negative charges. K is a constant and D is the distance between the charges. So we can talk about a coulomb of charge, and a coulomb of charge is 6.25 times 10 to the 18th electrons. And it's about the amount of charge that passes through a 100-watt light bulb in 1 second. If a pair of charges 1 coulomb each were a meter apart, the repulsion force would be about 9 billion newtons. But a net charge like that doesn't exist. Compare the last example to the gravitational forces between the two masses, 1 kilogram each, 1 meter apart, and you only get that many newtons. So that's just an example of how electricity and gravity, electricity wins. Gravitational forces between ordinary objects are too small to be detected, but electrical net forces between two objects are definitely large enough to be detected. Both are inverse square laws. Gravitation only attracts, while electrical can be attractive or repulsive, but they have that same formula shape. Conductors and insulators, you probably know a little bit about that. I'm going to go through that pretty quickly. Semiconductors are kind of interesting because they're good insulators in pure form, but only if one atom is replaced in 10 million, and then they become conductors. And near absolute zero, some metals will get infinite conductivity, so they're considered superconductors. Talked a little bit about getting shocked, building up the electrons, and a good conductor will get these electrons, spread them all over itself. An insulator maybe you need touched at several places to get the electrons spread out. I'm going to talk a little bit about charging by induction. Again, this is probably ninth grade science stuff. Okay, electric fields, a space around a magnet is different than if the magnet wasn't there. So if you put a paper clip in it, it wouldn't move. But if a magnet were there, it would. Space around a black hole is different than if the black hole wasn't there. And just that, in the same way that the space around the concentration of electric charge is different if the electric charge wasn't there. So these spaces contain force fields. An electric field has magnitude and direction. Magnitude is measured by the effect its charge is located on the field, and the direction is the electric force on a small positive test charge. So you kind of think if you took a little proton or something like that and threw it in there, you could tell the direction the force field is going from what the positive test charge is doing. The positive obviously will go away from the positive and toward the negative. And if you draw the vector longer, that's going to indicate a stronger field line. So here's some pictures of an electric field. So if I threw a small test charge, a positive test charge, what would happen? It would go from the positive be repelled and go toward the negative. And here would be a close-up picture of going from positive to negative. Electric shielding, if there's an electrical storm or there are live wires, you actually are safe in your car. This would be kind of a shield, as long as you don't go out of the car. This would kind of shield you. And a lot of electronics are cased in metal coverings to shield them from outside activity. Okay, so getting to kind of the math part of it, we're going to talk about electric potential energy. And electric potential energy it's really actually a very physical thing. If we put a positive charge in there and we try to push it toward the positive part, it doesn't want to go. We have to put work into that. We have to put energy into that to make it go. If we release it, it's going to accelerate from the source, and all that work we did to kind of push it toward the positive will get changed into electric. Electric potential energy here is going to be electric potential energy in joules over coulombs of charge. So some examples here. Oh, the SI unit for this is the volt, potential energy, or sometimes referred to as voltage. And a volt is going to be 1 joule per coulomb. So for example, if a conductor has a potential of 1,000 volts, it would take 1,000 joules of energy per coulomb to bring that charge from far away and add it to the conductor. How much energy to add the charge of 1 proton to this conductor? So if you had 1,000 joules, so if you had 1,000 joules per coulomb, okay, so that's 1,000 volts right there. And we're saying, well, what if we only had this many coulombs of charge? How much work would it take to push that toward towards something it didn't want to go towards? So if it was a positive, towards a positive. And also, how much energy would we have if it were to be released? Well, we'd have this many joules of kinetic energy. So let's just talk about if we did 20 joules of work to push 0.005 coulombs of charge, what would the voltage difference be? And basically, I'm going to take that 20 joules and divide it by 0.005 coulombs, and that would give me my voltage, 4,000 volts. All right. Twice as much charge would cause the object to have twice as much electric potential energy. The electric potential, though, would be the same. I know that gets a little bit confusing. The electric potential energy is really the joules and the work. The electric potential, though, would be the same, so the voltage would be the same. So I've got 1,000 joules per coulomb or 2,000 joules per 2 coulombs. It still has that same ratio, so the same voltage. The point here is that high voltage is only a problem if high charge exists. So sparklers are a good example of this. That we have these sparklers which can reach 2,000 degrees Fahrenheit. They're incredibly dangerous in that sense. But what kind of little sparks are coming off of that at that temperature? Well, they're so tiny that, yes, they're incredibly hot, but it's so tiny that they're not going to pose a great risk. So if you were to rub a balloon in your hair, it becomes negatively charged several thousand volts, say 3,000 volts. But it's only about 1 times 10 to the negative 6 coulombs of charge that gets transferred. So if I took that 3,000 volts, 3,000 joules per coulomb, I multiplied it by this many coulombs, I'm really only getting 0.003 joules of energy, so not particularly dangerous. Okay, storage, electric storage. Capacitors are found in nearly all electronics circuits. And basically, if you want to do a simple capacitor, you've got 2 conducting plates separated by a small distance, just not touching. And some pictures I'll show you here, you'll see some of those that we're going to be using. More voltage for the capacitor, more voltage from a battery. It just kind of depends on how much energy you've got stored, how strong that battery is, or how much power that battery has. Energy comes from work needed to charge it in the form of electric field between the plates. So these are some simple ones where basically you've got the two plates right here. They're rolled up with paper between them so they don't touch, and you can charge up some energy. These obviously are pretty little. You can have giant ones as well. Capacitance is charge, okay, that little Q that we looked at, could be a big Q, over voltage, V. The units are coulombs of charge over voltage, and that unit is farads. So, a parallel plate capacitor has a charge of 12 microcoulombs when charged by a potential difference of 2 volts. What's its capacitance? So I'm just going to make it simple here. I'm going to change it to coulombs. I'm not going to put it in proper scientific notation, but I've got 12 times 10 to the negative 6 over 2 volts. And so we're going to get 6 times 10 to the negative 6 farads. 6 times 10 to the negative 6 farads. Okay. You can also, whoops, do this one here. Nope. Okay. Do this one right here. So what if I had a 5 microfarad capacitor connected to a 12 volt battery? What charge can we look at? All right, well, first of all, let me take that and change it to farads, not microfarads. We'd have Q over 12 volts. And so then we could solve for the charge. We'd get 6 times 10 to the negative 5 coulombs of charge. Okay. Discharging a capacitor, a couple ways you could do that. Conducting path is put between the plates of the capacitor, but you could be it. It could be pretty shocking, fatal, even if the power supply is inside a TV. Even taking apart a TV, even when it's unplugged, you've got this capacitor charging up or storing energy, and you're taking it apart, and if it discharges through you, it actually can be a problem. You can discharge it through a long area, through metal wire, empty spaces. A Van de Graaff generator, you might have seen, builds up high voltages, and again, millions of volts can be generated, which sounds scary, but it's not that much charge, so it's dangerous. The flow of charge, recall that heat flows from hot to cold, the second law of thermodynamics, and in the same way, charge flows from the higher potential end of a conductor to the lower charge. And potential difference means charge flow. And the flow is going to continue until both ends reach a common potential. So a couple ways you could do that. You could connect one end of the wire to the ground and the other end of the Van de Graaff, and it's going to be very quick, a brief flow before common potential is reached. We want to get a sustained flow, though. We don't want to have our batteries discharged and they're all gone. We want it to be sustained. And so what we do is talk about electric current and electrical resistance. So I'm going to probably stop this, and we'll talk about electric current in the next video. Although at this point you should be able to do all the problems up through capacitance.